Hi everyone, this is part 2 of the issues with concentricity video. In this video we are using a real world part on the CMM, so we have live data, and the idea is just to show you how best to apply concentricity to your measurements on anything with an axis, i.e. it's not 2D, and just to go over again some of the finer details in how concentricity is supposed to be measured, but how it actually works out in terms of applying it in Aberlink3D. So let's move on to the next stage. So to start with, I have made a very simple drawing test for the part, and you can see on the left hand side is how it would be if all the callouts on the diameters. This is the data made diameter, and then in relation to this we want a concentricity check on the groove diameter, the outer diameter here, the outer diameter here, and also the internal diameter on the inside. Now we can measure concentricity this way, but there's a lot of different ways you can interpret this, and I would assume if you gave this drawing to 10 different people, you would end up with 10 different programs and also 10 different results. And the idea is we want to try and get that much lower than that, where the programs are repeatable across a range of different engineers programming the machine. And that's why on the right hand side I'll show you with the correct callouts, which are far easier to actually measure. We have all the cylinders measured with total runout to A, which will also be a cylinder. And then because the groove is very difficult to measure as a cylinder because it's so thin, we'll measure that as a circle and apply singular runout. So these are the two examples, and we're going to dive into the part now, and I'm going to show you the program data that I've gathered on the CMM. And we can start analysing the data. Before I show you the results from my program, it is worth just going through the fundamentals again. Once again, we are on gd&tbasics.com. Big shout out to them. I mentioned it in video 1, but they have a lot of useful stuff on that site. And in this example, you see a typical application of concentricity on a axis line or a spindle or a shaft. And you see here, data may spindle, and this reference feature B is wanting to be concentric to 0.2 millimeters to A. And in theory, the way that we measure this is we have a tolerance zone over the axis. The problem with concentricity is we need to actually touch the points on the outside of the feature. This fundamentally has to be a cylinder because the circles are 2D. So it can vary depending on whereabouts we measure, and this alone means that concentricity is, theoretically impossible to actually measure. It's always a guess from the CMM, touching the points on the outside of the job and then trying to work out whereabouts the central point is based on those external points. So it's always been an issue that concentricity is like a theoretical center point from data points taken on the outside of the feature. This alone obviously causes a lot of discrepancy between different software packages that use different algorithms. And the idea is with Aberlink, there's no fundamental way to actually apply this correctly, because what this is actually asking for is runout. The only difference is runout is also including the form of the outside shape rather than the theoretical axis line. So when we're measuring concentricity in Aberlink, when we're trying to work out this central point, we're having to measure it as a circle, and like I said, the circle has to be projected somewhere as it's 2D, and it would have to be in one of these faces, and then the position checked at a certain cross section. The moment we have to do an axis line like this, we are actually measuring runout. So hopefully that gives you a better understanding going into this exercise. And I'd also, I've mentioned it before, but the final note, as you can see on this website, avoid concentricity. It's so open and ambiguous, and you'll see from my examples in this next part, it's much better to apply runout and circular runout or singular runout. So let's dive into the example now. So we'll start off by covering some of the dilemmas we face immediately when trying to check this part with concentricity. So the idea obviously is with concentricity checks, we need A to be a circle, and we need the corresponding callouts. So this callout, this callout, this callout, and this callout also to be measured as circles. And the difficulty we have is how do we decide, just starting with A, let's say, whereabouts we measure it as a circle. Now, this is how we check it in Aberlink circle to circle. This is the way that a lot of other softwares use. But as we showed in the previous example on the gd&t website, we really need to try and measure the thing as an axis. And again, that's when we get into actually what we're measuring is runout. But if we do go down the concentricity route, we have this problem. So we need to decide whereabouts are we going to measure this circle, and then whereabouts are we going to use that 2D projection of the circle and project it into. Will it be this plane? Will it be this plane? Will it be this shoulder? Will it be the end face? And hopefully immediately already you can see why we have such a headache trying to get a fixed, steady answer to measuring concentricity, because I've already explained, 4 or 5 different ways we can do this. And that's where we end up with a lot of problems. Now, what I do find is if you really must follow the concentricity call out, one of the best ways to do it is still to set up using cylinders, but then use the construction method to do an intersection plane and an intersection circle. This was covered in the part 1 video, but I'll go over it again now. And this gives you a circle that is actually true to the diameter itself. So I mean, we're measuring this as a cylinder. It has its own axis, it has its own alignment, and the circle that we use for the datum and subsequent concentricity callouts are going to be true to itself. There's no skewing or projection issues. Okay, so let's have a look at that with a program. So this is the example program I've created. This is checking it in the nominal way. I would say this is the the best way to actually measure this spindle, and this was highlighted in the second drawing I made, where we're using runout and circular runout to test the part. The program itself has the datum A as a cylinder, that is the primary reference. We then construct a point where the cylinder meets the end face, that is our origin, and the rotation is taken care of by a line on the top of the hex. That does the x-axis rotation and finishes off the 6 degrees of freedom. And as you can see, you're getting a nominal, repeatable, more robust program by verifying runout, as it's aligning all the dimensions through datum A, so through this axis alignment, and then it's essentially running the clock along the entire outside profile. So it's not only taking into account the axis alignment, but also the form of the shape. This is really important for spindles and shafts, because if the diameter itself isn't round, say the diameter itself was like a hexagon, concentricity would still pass, but runout would fail, even if the axes were perfectly aligned. And obviously a drive shaft or a spindle not being round causes a lot of vibration, ultimately causing the thing to fail. So that's one really critical reason why I prefer runout over concentricity. So this just shows the nominal setup. However, you can actually highlight the setup that I'm about to cover with the circlip groove or the O-ring groove. So that's that there. So these are typically very difficult to measure as cylinders, and this is where we have to utilize the circle projection into the datum feature itself, just to align the dimension correctly. So we do measure this as a circle. This is the circle here. I'm going to show you some measurement tips later on how to actually measure the full diameter, even though the part is on its side. And you'll see I've projected this into feature number 8. So what is feature number 8? Well, we don't actually have a plane to project into anywhere near. The options would be measured planes on the front, the shoulder, or the rear shoulder, or the rear face, which are still, very far away on the axis in relation to this groove. So what I've done is I'm using datum A as that's the reference it's to. I'm using that to align it. and I'm constructing a plane. So this plane has been constructed from the cylinder. Yeah, so plane, spanner, double click your cylinder, and that constructs a plane perfectly 90 degrees to the axis, and we're using that for the projection. Now again, this is a bit ambiguous. I understand that some people, would prefer to put it into a measured plane. You can do this, but you always have to factor in that if the plane isn't 90 degrees to the feature you're measuring, you will get a skew, and it will skew the position and the form of the shape. So in this particular case, I've projected it into this plane, and the call out is simply the cylinder to the circle. And you see that gives us our 7 micron circular runout. And you see this image just on the call out. It's a single arrow, meaning it's a cylinder to a circle. So that is sort of the ideal world situation. We'll now look at setting up where we do the whole thing through concentricity. When we're measuring spindles or shafts, it's always worth remembering we want to try and take at least 15 points when measuring cylinders, at least 7 when measuring circles, and we need to try and measure the entire diameter. So in this particular case, you can see I've went for my preferred method of using A90 B0 and A90 B-180. Getting at it from 2 angles, this means you only need 2 probe angles and you're going to get the full sweep around the part. You obviously need good fixturing like this to be able to access the underside of the part as well. But if you're ever trying to measure this and you only can measure half of it because you're measuring at A0, B0, that will skew the results. So just bear that in mind. So if we are going to verify all the sizes via concentricity, the key is to construct planes and intersection circles on all the cylinders. So plane, double click the cylinder, that creates the plane. Circle, construct between the cylinder and the plane. OK. Plane, construct, double click the cylinder, green tick. Circle, construct, cylinder and plane, green tick. Repeat this for all of your cylinders. Circle, construct between the 2. I've already done one on the reference cylinder, so I just need to do the circle. Oh, sorry, that was the wrong one. Circle, construct, cylinder and plane. There we go. And we'll pick this constructed circle as datum A. And that's what we're going to reference. And what we're going to do now is basically dimension between this circle and the other circles. So circle and circle, and you'll see, you can call this out on here, circle and circle, circle and circle. Finally, circle and the O-ring groove circle. And hopefully you're starting to see the call outs. I'll try setting them next to the feature it's called out from. And you get the idea. And what you'll find is when we set up like this, because each circle is true to itself, i.e. its own bore, the skewing effect of trying to squash those circular points into a plane that may not be 90 degrees to it is really eradicated, and you're getting a much truer reading. So you'll see these tie in with your suspected readings much better than you would if you try to use an end face, use a shoulder face, or use a mid plane between the 2. Not that these aren't functional methods, but you just, in terms of actually getting a functional concentricity measurement, this is the best way to actually apply it in Aberlink3D. So hopefully that covers everything, but yeah, let me know if not, and I'd be happy to help. One final note to add that keeps, popping up in terms of people being puzzled with the sizes they see on the screen is dimension order. So the order in which you dimension is very important. This is the fundamental reason why datums are used. The datum feature gets selected first. That is the primary alignment, and then the theoretical clock runs along the second surface. So just to highlight that issue, if I go to A and this cylinder, I've got 13 microns. If I go the other way around, I end up with 8 microns, and that's because with A selected first, I'm aligning the error, or the clock, through this cylinder and running it around the entire length of this cylinder. This cylinder is longer, and if it's slightly out, which it is, the clock error gets bigger by the end of the entire surface, which is why we end up with 13. Doing it the other way around, we're aligning through this cylinder and only running the clock along this length of surface on datum A, which is obviously going to result in a smaller error. You have the exact same thing with circles as well. So we have the concentricity from this circle to this circle, 58 microns. If I do it the other way around, this circle to this circle, we end up with 561 microns, and that is behaving exactly as I would expect it. The alignment for the position is aligned through the initial plane. So because if you look at these two, this one is, just using the front face as a reference, 90.2 degrees, whereas the larger bow is 90. When we dimension this one first, it's aligning through here and checking out the the YZ positional error essentially to this circle, aligned through this plane. And if we do it the other way, because this is skewed, when this sort of squares itself up, this will be way further out, which is producing the much bigger concentricity error. Now, if you don't see any datums on your drawings, that will be a big red flag, because that is defining no dimensional order, and it's a bit of a free-for-all, completely up to you which ones you pick. So designers should always implement a datum call out on any runout, circular runout, or concentricity checks, and that dictates that you click on the datum first to do the alignment of the dimension. So that wraps up this series. Thank you very much.